Hey there, Mr. Sutton here, bringing you the Pre-Cal Honors 9-3 Part 2 homework solutions on algebraic limits of polynomial and rational functions. On this problem, we're trying to find the limit as x approaches 2 of this polynomial. Since it is a polynomial and it's continuous everywhere, plugging in is going to give us the limit. So just plug 2 in for all the x values. We've got, let's see, 6 times 8 is 48. Over here, this is 2 times 4, so that's minus 8. Plus 10 minus 3. So this is going to be 40 plus 10 is 50 minus 3 is 47. For this problem, I'm trying to find the limit as x approaches 4 of this rational function. Now, it's tempting to factor this x squared minus 16, but there's really not much point to it because you can see very quickly you're not going to get 0 in the denominator by plugging 4 in. So there really isn't anything you're going to need to cancel out. Let's just go ahead and plug this in right away. That'll be 4 squared minus 16 over 4 plus 3. So 16 minus 16 is 0. 4 plus 3 is 7. We can simplify that to 0. And since we're actually getting a number out of this, that means that this is the limit of our expression here. On this problem, I want the limit as x approaches 3 of this rational function. Now, I can see very quickly if I plug in 3, I'm going to have 0 in the denominator. So let me try factoring out things and see if anything cancels before I actually bother plugging 3 in anywhere. The numerator, I can factor into x minus 3 and x minus 4, multiplying to 12 and adding up to negative 7. And now I can actually cancel out those x minus 3's, leaving me with the limit as x approaches 3 of just x minus 4. At this point, I can plug 3 in here to give me negative 1 for my final answer. For this problem, I want limit as x approaches 4 of this rational expression. Now, it's tempting to factor this out, but I can see right away if I plug 4 in, I'm not going to get 0 in the numerator, so there's no risk of having a 0 over 0 situation. So I'm just going to go straight ahead and plug 4 in everywhere. So we have 4 plus 4 up top and 4 plugged in everywhere in the denominator as well. So that's 8 in the numerator. Down here I've got 16 minus 24 plus 8. That actually all comes out to 0. 8 over 0, I have a non-zero number over 0. That means I have a vertical asymptote, which means my limit automatically does not exist. On this problem, we want limit as x approaches 2 of this expression. Now, you can see pretty quickly just mentally plugging in 2 for x, you're going to end up with 0 in the numerator and denominator. So let's go ahead and just skip to the factoring and canceling part of this mess. The numerator, I can actually factor that. If I take a negative 1 out of that, that would give me x minus 2 inside. And I'm only doing that because it might be helpful with what I factor my denominator into. My denominator I can factor into x plus 2, x minus 2. So now this x minus 2 and this one can cancel out. That leaves me with limit as x approaches 2 of negative 1 over x plus 2. And since I've canceled something out, it's time to try plugging the number in for real. This will be negative 1 over 2 plus 2, or simply negative 1/4. On this problem, I want the limit as x approaches negative 2 of all this stuff. Now, this is a good candidate for factoring to see if we have anything that's going to give us 0 over 0 before I even bother plugging this in. So if I break this up, I can split my numerator into x plus 2 and x plus 3, things that multiply to 6 and add up to 5. Denominator, we need to multiply to negative 6 and add up to negative 1. So that would be positive 2 and negative 3. And now I see, yep, the x plus 2's are going to cancel. So I really just have the limit of x approaching negative 2 of x plus 3 over x minus 3. Now I'm going to go ahead and plug in negative 2. I'm clearly not going to get 0 over 0 if I do it now. So we've got negative 2 plus 3 up top, which is just 1. Negative 2 minus 3 in the bottom is negative 5, so negative 1/5. For this problem, we want the limit as x approaches 3 of this expression. Now I can see if I plug 3 in the numerator, I'm not going to get 0 up there. So I don't have to worry about factoring and canceling anything. I'm just going to plug 3 in everywhere and see if this comes out to a number or undefined. So we're going to have 3 plus 2 over 3 squared minus 9. That's 5 over 0. Since I have 0 in the denominator and I don't have 0 in the numerator, that means this is a vertical asymptote, so my limit does not exist. On this problem, I want the limit as x approaches -1 of this expression. Now I can see right away I'm going to have 0 in the denominator, and if you do a little mental checking, we've got 2 plus 1 minus 3. We're going to have 0 in the numerator as well. So let's go straight to seeing if we can factor this thing and cancel out some common factors. Now, when you're doing this, you could do some guess and check with the numerator, but you already know you're going to end up with a 0 up here. So that means this must factor into x plus 1 times something else. So x plus 1 times what would give me all this? Well, I'll have to have a 2x, and let's see here. If I've already got x plus 1, to get -3, I'm going to have a 2x minus 3. So that's going to be my other factor. And if we just double check this, we'll have 2x minus 3x gives us the -x in the middle. All right, now that we've got that factored, we can cancel out the x plus 1s. So that just leaves us with limit as x approaches -1 of 2x minus 3. Plugging in -1, that's 2 times -1 minus 3, which is going to give us -5. For this problem, we want the limit as x approaches 0 of this big expression here. Now, I can see pretty quickly if I plug 0 in, that's going to 0 everything out, and I'm going to end up with 0 over 0, which doesn't really help me narrow things down at all. So I'm going to go straight to the factoring and canceling step. I see in the numerator that I can factor out an x squared, leaving me with 5x squared plus 8. And in my denominator, I can take out an x squared as well, leaving me with 3x squared minus 16. The x squareds here are going to cancel. And that's, by the way, what was causing me to have 0 over 0 ultimately. This is 0 squared over 0 squared. So now just taking a look at what's left, plugging 0 into the remaining expression here, I'm going to have 5 times 0 squared plus 8 over 3 times 0 squared minus 16. These first terms just go away, and we've really just got 8 over -16, which I can reduce to -1/2. So that ends up being choice A. For this problem, I'm trying to find the limit as x approaches 2 of this expression. This looks like something that's pretty factorable, so I'm just going to go ahead and factor it and see what happens. So in the numerator, we can break this up into, let's see, I need numbers that multiply to -6 and add up to 1, so -2 and +3. Denominator, I can split this up into x plus 2 and x minus 2. So I see right away that if I had plugged 2 in the beginning, I would have gotten 0 over 0 because of these x minus 2's in the numerator and denominator. But now I'm just going to go ahead and cancel those out. I would have had to have done this anyway. So now I've got x plus 3 over x plus 2. Since I've canceled out the problem part here, I'm just going to plug 2 in for real now. This will be 2 plus 3 over 2 plus 2, which is 5 over 4. Answer choice D. For this one, we want to take the limit as x approaches 1 of x over ln of x. Now, this is a little bit weird, this ln of x. In a situation like this, there's nothing you can really do except plug in your number and hope for the best. So that's going to be 1 over the ln of 1. Now, the ln of 1, that's the number I have to raise e to in order to get 1. That's 0. So this is really just 1 over 0. And since this is giving us a vertical asymptote, that means that there is no limit on this one, d and e, so choice E is what we're looking for. On this oddball problem, we have a continuous function f that's increasing after -1, and then we've got this table with different values of f. Based off all this, they want an approximation for limit as x approaches 0 of e to the -2 times f of x. So e and -2, those are just normal numbers, but f of x here, this is where if you're plugging something in with this limit, this is where it happens in this f function. In order to figure out what all of this comes out to, we need to know the limit as x approaches 0 of f of x itself. For that, we're going to have to look at the table because we don't really have anything else to go on here. So for the table, we see that as we get closer and closer and closer to the x value 0, and from both directions this is happening, you'll notice the y values are also getting closer and closer to 0. So based off the table, we can say that the limit as x approaches 0 of f of x appears to be 0. Now there's a few caveats to this. Are we guaranteed that if we went even closer this pattern would hold? No, we're not. But we do know something. They told us that this function was continuous and increasing. That means that as we go from negative 0.001 to 0, our function is going up all the time, so heading towards the positive territory, and it's approaching 0. Are we guaranteed that we have exactly 0 when the function is at x equals 0? We're not, but it at least goes through 0 to get from a negative to a positive. So that's something. All right, so using 0 as our value, we can now write this limit expression that we started with as e to the negative 2 times 0. This is really just e to the 0, which is just 1. Choice C.